Thank you. Today I'm going to present our work verifying neural networks with PyRAT, which is a tool we developed with my colleagues at CEA, Augustin Lemesle, Tristan, Gall, and Zakaria, Chihani. So this is quite different from the other talk. It's based on AI, it's verifying AI. As you may have noticed, everybody talk about LLM and use AI, but they are also used in critical systems such as aeronautics, nuclear energies, health, and as such, they should be treated the same way as classical software used in a critical system, meaning they should be tested and validated. That is why we created our tool, PyRAT. So, PyRAT is verifying a certain type of architecture of AI. It's called neural networks. Basically, it's a succession of linear and nonlinear functions. Usually, the linear functions are matrix multiplication or convolutions, and the nonlinear functions are generally element-wise real functions, which are classical functions are the ReLU, the maximum between 0 and x, and the sigmoid. This is an architecture that is called layered. And now that is the thing that PyRAT will try to verify. The property we are considering is a global safety property. So given an input set and an output set, we want to apply the neural network to this input set and verify that the output set is the output set of the neural network is within the desired output set. We also consider a second type of property. It's called the local robustness property. You are given an input and a perturbation gamma, and you want the prediction of the neural network to be the same in the gamma neighborhood of this input. So this is basically what is used for high-dimensional non-structured data, such as images. How do we do that? So first of all, verifying neural networks is something that is hard. Indeed, it's an NP-complete problem for ReLU neural networks. So what we do is using abstract interpretation. In neural networks, what we do is that we have our property, which is the input set. We transform the input set with the first layer. We over-approximate this whole set, which gives us an approximate set, and we repeat this process, and we obtain an over-approximated output layer, which output of the neural network, which gives us three cases. Either you are in the entirely contained in the property, which means that you have proven your property. If you are entirely outside, it means that your property is false. But when you are in the case when there is an overlap between the two, since you are considering over-approximation, you cannot conclude. So PyRAT, which stands for Python Reachability Analysis Tool, takes into input three files: a property file, a neural network file, and a config file, which contains numerous different options for PyRAT. There is some processing steps and some analysis steps where there is the reachability analysis where we perform the abstract interpretation. So neural networks are represented. There is different formats. In PyRAT we support the main format, which is ONNX. We have also other formats, but this is more limited. We take these formats and transform them into our own internal representation of neural network to efficiently verify them. There is some operations are slightly modified to improve the efficiency for the verification later. And same for the property. There is one kind of format for the property. This is called the VNN-COMP format, We also design our own format for simplification to define a property, which is just X for the input and Y for the outputs. So with this, input set, we can perform abstract interpretation. In PyRAT, we implement many domains, intervals, symbolic intervals on the top, polytop, constraints on the top, hybrids on the tops. I'm going to talk to you about intervals on the tops and constraints on the tops. Keep in mind that while doing the over-approximation with all these functions, PyRAT is sound with respect to floating point operation, which is not something that is common with for the other neural network verifiers. So to illustrate these abstract domains, I'm going to use a toy network and property. So you have this little neural network. The property is you have x1 and x2 between -1 and 1, and you have to prove that the output is between -1.8 and 2.5. So for the intervals, it's just classical interval arithmetic, but just to quickly walk you through it. So you perform, for the top row, you perform 3 times -1, 1 plus 1 times -1, 1. You obtain -4, 4. The ReLU, you apply the ReLU to -4, 4, which is the maximum between 0 and -4, 4. You obtain 0 and 4. Same for the bottom row. You add them up. You obtain that the output is between -3 and 4, which is not enough to conclude. Thus, we need a more precise domains. So, sonotops, these are, if you are familiar with it, good, but if not, a quick walkthrough is that it is an affine transformation of an hypercube. It is represented by 2 parameters, parameters alpha and beta. You need a critical operation is the concretization. It's to transform it into an interval, because at the end you want to know if your property is proven or not, and you need to have bounds. This is easily computed for the sonotops because it's just the L1 norms. And you also need the concretization operation to over-approximate non-linear function. Because the sonotops is an affine form, and the nonlinear functions are by definition nonlinear, you need to over-approximate them to represent them. So the sonotop approximation of the ReLU, you need to have to add a new dimension to your hyperbox, to your hypercube, and you have new alpha prime and beta prime, which depends on the lower and upper bound of the concretization. So on the example, you get the result that the output is x1 over 2 plus epsilon 1. Epsilon 1 is the noise introduced to over-approximate the ReLU 1 minus 3/4, which is the same from the ReLU 2, plus a quarter. So now the output is between -2 and 2.5. It is closer, but still not enough. And for that, in PyRAT, we have the constraints on the top, which are the sonotops with affine linear constraints. So for the ReLU, since it's just the maximum between 0 and x, we just had the constraint that the ReLU is positive, and the ReLU is greater than x. With this constraint, now on the toy example, it creates 4 constraints, and now this is enough to prove our property. But what if the property was harder? What if our abstract domains were not enough to prove the property? A simple thing to do is to perform multiple analysis to have tighter bounds. So this is called Bunsen bounds on inputs. So you just, instead of taking between -1 and 1, you take the first one to be between -1 and 0. You prove that, and you do the same for the other part. You prove it. Now it's easy to parallelize, and we can leverage GPUs. but this is something that scales with the number of input dimensions. So this is hard to verify in practice for high input dimensions. So we have a second thing in PyRAT to circumvent that. Is to split on role use. It is a nonlinear function, but you can consider it either to be, if you are in the negative case, you only consider the role use to be 0, and if you are in the positive case, it is just the identity functions. So these are linear constraints, so you can handle that with constraints on the tops. And similarly to branch and bound on inputs, you can prove them. You can also parallelize them and leverages GPU. But now this is dependent on the number of role use and not on the number of inputs. So this is the overall mechanism of PyRAT. But with this multiple analysis, you will be able to falsify your property if it is false. But what we find more efficient is to have a counterexample search strategy. So we just define a distance and we minimize that with some optimization, so that when we perform multiple analysis, at the end of each reachability analysis, we run this algorithm to try to provide us with a counterexample. Now that I have presented you with all that is done in PyRAT, how can you test and evaluate PyRAT? There is an artifact available on Zenodo. And for research purposes, you can contact us and we'll provide with you with a free license, because due to politics at CA, our code is closed source. But once you have your license, the installation is really easy. You just get all your packages with PeopleStat and you are ready to go. So just to highlight some of the capacity of PyRAT, there is an annual neural network verification competition. We participated in the last 3 competitions. We each time got the podium. There is a large range of neural network that is tested in this competition. As you can see, input dimensions are ranging from 1 to 1 million. The number of parameters in the neural network are ranging from 500 to multiple millions. So our tool is really competitive. I just want also to show you a quick industrial use case. So this is from a joint work with Airbus. There is a paper on it. So they had drones, and they had lookup tables that for each value in the lookup table that said if there is an intruder in this zone, you have to either go left or go right or go straight. But these tables were 30 gigabytes, and these tables were supposed to be embedded in drones, but they took up too much space, too much memory. So what they wanted to do was use neural network, but they needed to certify the neural network because they didn't want their drone to crash. So we managed to prove that 85% of the neural network matched with the lookup table. So they built a hybrid system with 85% of the neural networks and the 15% left of the table. It went down to 5 gigabytes, and that could be embedded in drones. So with all that, we still have many things to do on PyRAT. I just shown you that we are splitting on ReLU, but we are not actually able to split yet on other nonlinear layers, such as the sigmoid functions. There is also an ongoing effort to handle other AI architectures such as transformers and RNN. And we are also trying to address embedded AI systems with our work with the edge platforms. So, meaning that we are trying to handle better the integer and floating operation. Thank you for listening.
Oops. Okay. I am not entirely clear on the way you do the splitting. So I understand that you try to identify the branching point, which I see fairly well how it would work for the first layer. Now, if you have, say, 5 layers and you want to do this on one of the last layers,
so you mean
kind of
for the ReLU, you mean?
Yes.
Yeah. Okay. Actually, we can do indeed everywhere. If I remember correctly, there is indeed what we are using is that we are using some heuristic to have a score to determine which ReLU do we want to split. Same for inputs, we have a score to determine which is the best to split on. For the ReLU, it is quite similar to the input. Is that we have a heuristic that score with the noises that are introduced, because what we interpret is that epsilon1 represents kind of the effect of the over approximation of the ReLU. So whichever of the coefficient is the bigger in the last in the output, we consider the split. Well, there is also some other operation done to perfect this heuristic, but the gist of it is that. So it's not always on the first layer or in the last layer, but if I remember correctly, I think it's most of the time kind of the first layer.
I see. Okay, actually, behind my question, I was actually wondering whether you would have cases where you want to you should do some splitting with respect to, say, the third layer, and that would get you to do more splittings on the second layer and then in turn to the first. But I don't think this seems to be happening, right?
Well, just to be sure, you are saying that if we split in the later layer,
whether splitting on the later layer would let you infer more adequate splittings on the first layers, or whether it's just one pass.
I think on that point, you are right.
Okay.
Yeah.
Thank you.
Thank you.
Any other questions? I do have a simple one.
Yeah.
At the beginning, you said that there is n plus 1 linear functions and n non-linear functions.
Yeah.
So, what's the typical size of n?
It's true that it really depends, but generally, I don't think we have like L bigger than 30 or 50. It's never more than that. But it can be just, if L is 1, yes, it just in the competition there are some network where the L is just 1, so just a linear function, a non-linear function, and a linear another linear function. So a small networks. But yeah.
And is there always one more linear function and non-linear? That's a given?
Well, it's just the way I presented it. We handle kind of other things, but it's just a neat representation for the definition.